Welcome to this module. Today we are going to see about multicast routing and we will discuss about the idea of optimal routing common in all multicast protocols. The process of optimal interdomain routing eventually results in the finding of the shortest path tree. The root of the tree is the source and the leaves are the potential destinations. The path from the root to each destination is the shortest path. The number of trees and the formation of trees in unicast and multicast routing are different. When a router receives a multicast packet, the situation is different from when it receives a unicast packet. A multicast packet may have destination in more than one network. Forwarding of a single packet to members of group requires the shortest path tree. If we have n groups, we may need n shortest path trees. We can imagine the complexity of multicast routing, and two approaches have been used to solve this problem. One is source-based tree and group-based trees. In the source-based tree approach, each router needs to have one shortest path tree for each group. The shortest path tree for the group defines the next hop for each network that has loyal numbers for the group. For example, if we assume that we have only 5 groups in the domain, say for example G1, G2, G3, G4 and G5. At the moment G1 has loyal members in 4 networks, G2 in 3, G3 in 2, G4 in 2 and G5 in 2. The name of the group with the loyal members on each network also shows the multicast routing table for router R1. There is one shortest path tree for each group. Therefore, there are 5 shortest path trees for 5 groups. If the router R1 receives a packet with a destination address G1, it needs to send a copy of the packet to the attached network, a copy of router R2 and a copy of router R4 so that all members of G1 can receive a copy. So in this approach, if the number of groups is m, each router needs to have m shortest path trees, one for each group. And we can imagine the complexity of routing table if we have hundreds or thousands of groups. Now we'll show how different protocols manage to alleviate these situations. And the second case is group shared tree. In group shared tree approach, instead of each router having m shortest path trees, only one designated router called the center core or endogenous router takes the responsibility of distributing multicast traffic. The core has m shortest path trees in its routing table. The rest of the routers in the domain have none. If a router receives a multicast packet, it encapsulates the packet in a unicast packet and sends it to the core router. The core router removes the multicast packet from its capsule and consults its routing table to route the packet. During the last few decades, several multicast routing protocols have emerged, and some of these protocols are extensions of unicast protocols, that is, others are totally new. Now let's move on to one by one. You can see in this diagram, and it is the taxonomy of these protocols are multicast broadcasting protocols are divided into source-based tree and group-shared tree. The source-based tree is further divided into MOSPF, DV, MRP and PAM. PAM is again divided into PAM, DM and PAM, SM, which comes under group shared tree. Group shared tree also has another leaf called CBT. We said that each router creates a shortest path tree by using Dijkstra algorithm, and the routing table is a translation of the shortest path tree. The multicast link state routing is a direct extension of the unicast routing and uses a source bus based tree approach. Although unicast routing is quite involved, the extension to multicast routing is very simple and straightforward. We can recall that in unicast routing, Each node needs to advertise the state of its link. For a multicast routing, a node needs to revise the interpretation of a state. A node advertises every group which has any loyal number of link. Here the meaning of the state is what groups are active in this link, and the information about the group comes from IGMP. And each router running IGMP solicits the host on the link to find the membership status. When a router receives all these LSPs, it creates n topologies. That is, n is the number of groups from which n shortest path trees are made by using Dijkstra algorithm. So each router has a routing table that represents as many shortest path trees as there are groups. The only problem with this protocol is the time and space needed to create and save the many shortest path trees. The solution is to create the trees only when needed. When a router receives a packet with a multicast destination address, it runs the Dijkstra algorithm to calculate the shortest path trees for that group. The result can be cached in case there are additional packets for that destination. And now let's move on to MOSPF, that is multicast open shortest path first. That it is a protocol which is an extension of the OSPF protocol that uses the multicast link state routing to create source based tree. The protocol requires a new link state update packet to associate with the unicast address of a host with a group address or address the host is sponsoring. And this packet is called group membership LSA. In this way, we can conclude in the tree only the hosts that belong to a particular group, that is using the unicast address. In other words, we make a tree that contains all the hosts belonging to a group, but we use the unicast address of the host in the calculation. For efficiency, the router calculates the shortest path trees on demand when it receives the first multicast packet, and in addition, the tree can be saved in cache memory for future use by the same group or group pair. MOSPF is a data-driven protocol, and the first time an MOSPF router sees a datagram with a given source and group address, the router constructs the Dijkstra shortest path tree. And now, let's see the multicast distance vector DB MRP with the multicast address. And unicast distance vector routing is very simple. Extending it to support the multicast routing is complicated. Multicast routing doesn't allow a router to send its routing table to its neighbors. The idea is to create a table from scratch by using the information from the unicast distance vector tables. Multicast distance vector routing uses source-based trees, but the router never actually makes a routing table. When a router receives a multicast packet, it forwards the packet as though it is consulting a routing table. We can say that the shortest path tree is evanescent, and after its use, the table is destroyed. After a packet is forwarded. So to accomplish this, the multicast distance vector algorithm uses a process based on 4 decision making strategies. Each strategy is built on its predecessor, and now we'll see one by one and see how each strategy can improve the shortcomings of the previous one. And the first case is flooding. Flooding is the first strategy that comes to mind. So a router receives a packet without even looking at the destination group address, sends it out from every interface except the one from which it was received. Flooding accomplishes the first goal of multicasting, that is, every network with active members receives the packet. Still, so networks without active members now we'll see, and this is a broadcast, not a multicast. So there is another problem, it creates loops. So a packet that has left the router may come back again from another interface, or the same interface be forwarded again. Some flooding protocols keep a copy of the packet for a while and discard any duplicates to avoid loops. And the next strategy is reverse path forwarding, corrects this defect. Reverse path forwarding is a modified flooding strategy. To prevent loops, only one copy is forwarded and the other copies are dropped. In RPF, a router forwards only the copy that has traveled the shortest path from the source to the router. To find this copy, RPF uses the unicast routing table. The router receives a packet and extracts the source address, and it consults its unicast routing table as though it wants to send a packet to the source address. The routing table tells the router the